Helium is cheap. You know that, right? You can walk into any store that sells party supplies, hand over a couple of dollars, and they will fill a balloon with helium for you. Your kid lets go of the string, the balloon floats up into the sky. Everybody waves goodbye and nobody thinks twice about it. $1.50 and a wave, that is what helium is worth to most people. Let me tell you what happens to that balloon, by the way. It rises because helium is less dense than air, just as a bubble rises in water. It keeps going up, and as it climbs, the atmospheric pressure drops and the balloon expands. Eventually, at some altitude, maybe 10 or 15 kilometers, the balloon bursts. The helium spills out and mixes into the surrounding air. From there, the helium atoms begin a slow, invisible migration upward, through the troposphere, through the stratosphere, up through the mesosphere, into the thermosphere. They get battered around by collisions with other molecules, heated by ultraviolet radiation, carried by winds. And eventually, over a span of time, that might be a few 100,000 years or 1,000,000 years, those helium atoms reach the exosphere and escape the planet. The child waving goodbye to the balloon has no idea that they are waving goodbye to something that will leave the Earth forever. And why would it be worth more? Helium is the second most abundant element in the entire universe. 24% of all the visible matter that exists in every galaxy, in every star, in every nebula is helium. There is so much helium out there that it is almost embarrassing. You would think we would be swimming in the stuff. You would think we could never run out if we tried. That is completely wrong, and I do not mean a little bit wrong. I mean spectacularly, dangerously, irreversibly wrong. And what makes it worse is that by the time most people realize how wrong it is, the helium will be gone. Not hard to find gone, not expensive gone, gone from the Earth forever, drifting away into the vacuum of space where no one will ever use it again for anything. Gone like a letter you threw into the ocean. Gone like heat dissipated into the cold night sky. Gone in the thermodynamic sense, the irreversible sense, the way physicists use the word gone. So let me tell you the real story of helium. Because it involves nuclear physics, it involves the sun, it involves the deep interior of the Earth, it involves some of the most important technology in modern medicine, and it involves one of the greatest acts of carelessness in the history of civilization. Let us start with what helium actually is, because even this most basic question is more interesting than people realize. Helium is an atom. 2 protons in the nucleus, 2 neutrons sitting in there with them, and 2 electrons whipping around the outside. That is it. Nothing fancy. It is so simple that it barely does anything. It does not form molecules. It does not combine with oxygen. It does not bond with carbon or nitrogen or any of the other elements that make up the interesting chemistry of life. It does not even bond with itself. 2 helium atoms sitting next to each other feel an attraction so feeble, so pathetically weak, that it takes almost no energy at all to pull them apart. The chemists call it a noble gas, which is their polite way of saying it refuses to participate. Its electron shell is full, 2 electrons, and they fill up the first energy level completely. There is no room for sharing, no empty slots to entice a neighbor. Helium is chemically complete. It needs nothing from anyone. If atoms had personalities, helium would be the one standing in the corner at the party with its arms crossed, not interested in conversation. And that personality, that aloofness, is what makes helium both incredibly useful and incredibly vulnerable. Because it does not react with anything, helium is invisible, odorless, tasteless. You cannot tell it is there unless you have the right instruments. If you breathe it in, your voice goes up because sound waves travel faster through a lighter gas. People think that is hilarious. But that party trick hides something deeply important about helium's nature. It does not stick to anything. It does not form chemical bonds with the rocks, the water, the soil. There are no helium minerals. There is no helium cycle the way there is a carbon cycle or a nitrogen cycle or a water cycle. Every other important gas in our atmosphere has chemical or biological pathways that keep it circulating, keep it anchored to the planet in one form or another. Helium has none of that. Zero. Once a helium atom reaches the upper atmosphere, nothing is holding it here. No chemistry, no biology, just gravity. And gravity for an atom this light is not enough. Let me explain why. Because the physics of this is fundamental, and it is beautiful, and it is the key to understanding why helium disappears. Every gas is made up of particles that are constantly in motion. They are bouncing off each other, bouncing off the walls of whatever container they are in, zigzagging around in a frantic, chaotic dance. That motion is what we mean by temperature. If I tell you a gas is at 300 Kelvin, what I am really telling you is something about the average kinetic energy of the particles. Hotter gas means faster particles. But here is the crucial detail. In any collection of gas molecules at a given temperature, the particles are not all moving at the same speed. There is a distribution of speeds. Most of them cluster around the average, but some of them, just by the luck of random collisions, are moving much faster than average, and a few of them out in the tail of the distribution are screaming along at extraordinary velocities. This is the Maxwell-Boltzmann distribution, and it is one of the most important ideas in all of physics. It tells you that in any gas, there will always be some fraction of particles moving faster than any speed you care to name. The fraction gets smaller as the speed gets higher, but it never reaches zero. There are always a few speedsters way out at the extreme end. Let me give you an analogy. Imagine a room full of people dancing. Most of them are swaying gently, more or less at the same pace. But every once in a while, two dancers collide and one of them gets flung across the floor much faster than the average. If you watch long enough, you would occasionally see someone moving so fast they crash right through the door and leave the building. In a room full of heavy people, that almost never happens because it takes too much energy to accelerate a heavy person to that speed. But in a room full of very light people, it happens more often because a light person who gets a lucky collision can reach tremendous speed. That is more or less what happens in the upper atmosphere, except the building is the Earth, the door is the edge of the gravitational well, and the people are gas molecules. For a heavy molecule like nitrogen, which has a molecular mass of 28, or oxygen at 32, even the speedsters in the extreme tail are not fast enough to escape the Earth's gravity. The escape velocity from the surface of the Earth is about 11 kilometers per second. That is roughly 25,000 miles per hour. At the temperatures found anywhere in the atmosphere, the number of nitrogen or oxygen molecules reaching that speed is effectively zero. They are stuck here, gravitationally bound to this planet for as long as the Earth exists. But helium is light. Devastatingly light. An atom of helium has an atomic mass of 4. That is 7 times lighter than nitrogen, 8 times lighter than oxygen. And because kinetic energy is shared democratically among particles at the same temperature, a light particle must move faster than a heavy one to carry the same energy. The equation is simple. Kinetic energy equals 1/2 times mass times velocity squared. If the mass goes down by a factor of 7, the velocity goes up. Not by a factor of 7, but by the square root of 7, which is about 2.6. Helium atoms, at the same temperature as nitrogen molecules, are moving nearly 3 times faster on average. That alone does not get them to escape velocity, not at ground level. But the upper atmosphere is a different story. Up at the exosphere, hundreds of kilometers above the surface, the gas is extremely thin. Collisions between molecules are rare. And the molecules that do reach up there are exposed to intense ultraviolet radiation from the sun, which pumps energy into them. At those altitudes, some helium atoms genuinely reach speeds exceeding the escape velocity. And when they do, they follow a hyperbolic trajectory outward away from the Earth and they never come back. There's another mechanism too, one that accounts for most of the helium loss. It is called the polar wind. The Earth's magnetic field, which shields us from the solar wind, has an interesting geometry near the poles. The field lines are open there, they reach out into space instead of looping back. Charged particles can follow these open field lines like marbles rolling down a track. Ionized helium atoms, helium that has been stripped of an electron by ultraviolet light, get caught in these open field lines and are funneled out into space through the polar regions. The Earth loses roughly 50 grams of helium every single second through these mechanisms. That does not sound like much, but it adds up. Over geological time, it is a relentless hemorrhage. The planet is slowly, continuously bleeding helium into the void. And here is the thing that should bother you deeply. The Earth does not have much helium to spare. The atmosphere of Earth contains about 5.2 parts per million of helium. That is almost nothing. 5 out of every million molecules in the air you are breathing right now are helium. Compare that to nitrogen at about 78% or oxygen at about 21%. Helium is barely there, a trace, a whisper. The universe is drenched in helium, but the Earth has almost none. Why? Because the Earth is too small and too warm. Jupiter has massive amounts of helium. Saturn, too. These gas giants are so enormous that their gravitational fields are overwhelming. A helium atom on Jupiter is not going anywhere. But the Earth sits in this awkward zone where gravity is strong enough to hold on to the heavy gases for billions of years, but not strong enough to keep a firm grip on helium. Over the 4.5 billion years since the Earth formed, most of the primordial helium that was here at the beginning has escaped. We are left with what the planet makes fresh through radioactive decay, and even that is constantly leaking away. So let me tell you where the helium that we actually use comes from, because the answer is stunning. Deep beneath the crust of the Earth, scattered through granite and basalt and sandstone, there are atoms of uranium and thorium. These are the heaviest naturally occurring elements. Daddy-o shacking. They are unstable. They have been decaying since the Earth was born, slowly transforming into lighter, more stable elements through chains of radioactive processes. One of the primary ways these heavy nuclei decay is through alpha decay. An unstable nucleus ejects a little bundle of particles, 2 protons and 2 neutrons tightly bound together. That bundle flies away from the parent nucleus at tremendous speed, typically about 5% of the speed of light, and slams into the surrounding rock, losing its energy in a fraction of a second. Let me describe what this looks like at the atomic level, because I want you to feel the strangeness of it. Somewhere deep in a granite formation, maybe a mile below your feet, there is an atom of uranium-238. It has been sitting there since before the dinosaurs existed. For hundreds of millions of years, it has done nothing. And then at a moment that no one can predict, with no external trigger, no warning, it decays. The nucleus reshuffles itself, and out pops an alpha particle moving at 15,000 kilometers per second. That particle plows through the crystalline lattice of the rock, colliding with atoms along its path, leaving a tiny trail of ionized material behind it, and comes to rest just a few hundredths of a millimeter from where it started. It grabs 2 electrons from the nearest available atoms, and it becomes helium. Just like that. A helium atom born from the death of something ancient. And this is happening right now as I speak. Under every continent, under the ocean floor, scattered through the crust and mantle of the Earth, uranium and thorium atoms are decaying, one by one, each one producing a single helium atom. 3,000 metric tons a year, total. It sounds like a lot, but spread across the volume of the entire planet, it is a trickle. A slow, patient geological drip that has been running since the Earth was born. Now here is the remarkable thing. That bundle, that alpha particle, is a helium nucleus. Exactly a helium nucleus. 2 protons, 2 neutrons. Within microseconds, it grabs a couple of electrons from the atoms in the rock around it, and it becomes a neutral helium atom. A full ordinary garden variety helium atom, identical in every way to the helium in a balloon, born from the nuclear disintegration of uranium. Every helium atom you have ever encountered was made this way. It was not here when the planet formed. It was manufactured, atom, by the slow ticking of nuclear clocks buried in the rock beneath your feet. About 3,000 metric tons of helium are generated this way every year throughout the entire Earth's crust. That sounds like a lot, but spread across the volume of the whole planet, it is a trickle. Some of that helium seeps upward through cracks and fissures in the rock and escapes directly into the atmosphere, where it promptly begins its slow drift upward, an eventual departure from the planet. This is the default. This is what happens to most helium produced by radioactive decay. It leaks out of the rock, floats up and leaves the Earth, vanishes into the cosmos. But some of it, by geological luck, gets trapped. It rises through the rock and encounters what geologists call a cap rock, an impermeable formation, like a dome of shale or anhydrite or salt that acts as a ceiling. The helium cannot penetrate this barrier, so it accumulates there, pooling in the pore spaces of the rock below, usually mixed in with natural gas, mostly methane, sometimes with nitrogen as well. These underground reservoirs are like natural storage tanks that the Earth has been filling for an almost incomprehensible length of time. Some of these deposits have been accumulating helium for 200, 300, 400 million years. Think about what that means. While the first land animals were crawling out of the oceans, while the continents were assembling and breaking apart, while entire ecosystems were evolving and going extinct, helium was slowly, steadily collecting in these underground chambers. Each deposit is a geological time capsule, a record of hundreds of millions of years of radioactive decay, captured by nothing more than a fortunate arrangement of permeable and impermeable rock layers. That is where we find it when we drill for natural gas in certain places. The gas that comes up contains a fraction of a percent of helium. In the richest deposits, concentrated in parts of the American Southwest, Algeria, Qatar, and Russia, you might find concentrations up to 7%. But in most natural gas fields, the helium content is well under 1%, too little to bother extracting. And in many operations, nobody does bother. The helium gets burned off with the methane or vented straight into the atmosphere. Wasted. Let me make sure that point lands. There is no way to make helium in a factory. You cannot synthesize it from simpler ingredients. There is no chemical reaction that produces it. You could in principle fuse hydrogen in a reactor and that would create helium, but we do not have working fusion power plants, and even when we do, the helium produced will be modest compared to what we consume. You could bombard lithium with protons in a particle accelerator, and occasionally a helium nucleus pops out, but the energy cost is absurd and the quantities are laughable. The only practical source of helium on this planet is the slow radioactive decay of uranium and thorium, a process that has been running for billions of years, trapped by geological formations that took millions of years to develop. We are spending an inheritance that was accumulated over the entire history of the Earth. We are living off geological interest that was compounded since before life existed on this planet, and we are burning through it in generations. Now let me tell you why that matters in a way that is more than abstract, because helium is not just a gas that makes balloons float and voices squeak. For several of its most critical applications, there is no substitute. None. The single largest use of helium is in cryogenics, the science of extremely low temperatures. Liquid helium boils at 4.2 Kelvin. Let me put that in terms you can feel. Absolute zero, the lowest temperature that is physically possible, the temperature at which all thermal motion stops, is 0 Kelvin. Liquid helium exists at just 4 degrees above that limit. That is roughly minus 269 degrees Celsius. You were minus 452 degrees Fahrenheit. Nothing else gets that cold in liquid form. Liquid hydrogen boils at 20 Kelvin. Liquid nitrogen, which most people think of as extraordinarily cold, boils at 77 Kelvin. Helium is in a class entirely by itself. It has the lowest boiling point of any substance in nature. And more than that, helium is the only element that remains a liquid all the way down to absolute zero at normal pressure. Every other substance freezes solid well before you get that cold. Helium refuses. It remains a liquid sloshing around, even at temperatures where the atoms are barely moving at all. And at those temperatures below about 2.17 Kelvin, something happens that I find more wonderful than almost anything else in physics. The liquid undergoes what we call the lambda transition, named after the shape of the graph of specific heat versus temperature, which looks like the Greek letter lambda. Below this temperature, helium becomes a superfluid. The discovery of superfluidity was one of the great surprises